So this week we are going to be beginning a new chapter, and actually we're probably going to cover all of chapter 10 this week. That can be your goal, is to get in all of the videos for chapter 10. Hopefully the exam went well for you. If it didn't, you can go back and review the answers and review the problems. Some of those may come back on the final exam, so take it as kind of a point of note when the final comes up. And we're going to be shifting gears a little bit. We talked about gases when we finished up chapter 9. Now we're going to combine the other two phases, and we're going to look at liquids and solids in this chapter. We're going to sort of look at all the phases to start out with again, compare them a little bit. Then we'll talk about liquids, then solids. And actually this chapter isn't too bad. It's conceptual. There's not a lot of math to it, and I think it'll make for some good videos. So we've got liquids and solids. When we're looking at the difference between liquids and solids versus gases, we're looking at particles that now do interact with each other. We said gases have particles that don't interact. The space between particles is large, right? So there's no attraction between particles. With liquids and solids, there is, and that's what this video is going to be about. So solids versus liquids, though, there's a little bit of a difference, and you guys know it. Maybe you imagine ice versus liquid water. There is some difference, and we talked briefly about that earlier. With solids, we say that that particles are tightly packed. There is a regular arrangement of the particles. And there's not much movement of the particles allowed. There's maybe some little vibration that the particles can show, but they can't really move around and they can't really move past each other. So they are fixed in a position, but may vibrate a little bit about that fixed position. So a little bit of vibration about a fixed position. Okay, the particles have fixed positions. Liquids, on the other hand, are still sort of tightly packed. They're in contact with each other. Particles are in close contact. But there is no regular arrangement. The molecules are allowed to move past each other and flow at a smaller scale, the same way that we look at it as having a flow in a larger scale. We see that water can flow, right? We see that in rivers and in faucets, right? We just see the water is able to flow out of a faucet. I realize I misspelled something here. Particles are in close contact. There's no regular arrangement. And molecules or particles can flow past each other. Okay, so we kind of have a separation here of the two sort of phases that we're looking at. And we're going to start talking about what forces there may be, what attractions there are, because these particles are so close together, what attractions there are between particles in liquids and solids. And these attractions we're going to call intermolecular forces. And that's what this whole video is going to be about. And we're going to continue to think about it in the rest of the chapter, but we're going to dig into it here. So intermolecular forces defined are forces of attraction between particles in a liquid or a solid. Forces of attraction between particles of a liquid or a solid. Some intermolecular forces are strong and hold the particles together very tightly. So maybe strong intermolecular forces would lend themselves to creating a solid structure. Weaker intermolecular forces make it possible for molecules to kind of move around a little bit, and they're still connected, but not tightly packed. Okay, so there's some varying strength of these forces, and we're going to talk about that. So when we're considering the phases of different substances, right, we've got solids, liquids, and gases. The phase that you observe for a particular substance is going to be a combination of how strong is the intermolecular force. Okay, so increasing intermolecular force goes, the weakest is for gases, and we even say there's no attractive force in the gas. No IMF, okay? No intermolecular force. Then as intermolecular forces can grow stronger, we see particles become in contact with each other. So we get this liquid, right? But still maybe the particles can move around a little bit and flow past each other. Then as we increase the strength yet of the intermolecular force, perhaps those particles become locked in position. Okay, there's not much movement allowed. The other factor that can depend or that can determine the phase of the substance, and we see this with the transitions between solid, liquid, and gas for water. I use water a lot because it's one that we are familiar with, maybe most familiar with. Is the amount of kinetic energy or the temperature of the substance. So if I have a lower temperature, right, so this is going to show increasing temperature from left to right. The lowest temperature or the least amount of kinetic energy is going to be shown in the solid substance. So think of ice, right? We put the water in a freezer where it's the lowest temperature of the three. Then as we increase temperature, we start to see the liquid phase, right? More kinetic energy present in those molecules. And then as we continue to increase the temperature even more, we start to see that evaporate and we get gas phase molecules. And essentially, the increased temperature is allowing us to overcome whatever intermolecular forces are there. If there are forces holding particles together, for us to be able to change phases, we need enough energy to break those intermolecular forces. Okay, so there's a balance when we see different phases. There's a balance between how strong is the IMF, how attracted are the particles to each other, and also how much energy is there. I do want to draw a distinction between intermolecular forces and intramolecular forces. Intramolecular forces will be forces within a molecule. So if I'm gonna write this out, intermolecular forces are what we said just a moment ago. Intermolecular forces are forces of attraction between two molecules, or multiple, but we'll say between two molecules. Okay, that might be like this dotted line where we have an HCl molecule and an HCl molecule. This interaction between one molecule and the other is an intermolecular force. two separate molecules have an attraction for each other. Intramolecular forces would be the force that's holding atoms together to make one molecule. Okay. In the past, we've referred to them as bonds. So these are going to be forces of attraction within one molecule. Okay? Within one molecule, they're the forces that hold the molecule together. And what the other thing that I might describe it as is a bond. Okay. So in this case, the intramolecular force is the thing holding the attraction holding this HCl molecule together between the chlorine and the hydrogen of the same molecule. So intramolecular force is the bond that holds that molecule together. Okay. And then and also this video is only going to be, we've talked a lot about bonds, so this one's only about intermolecular forces, and the main point of this is just saying it's not going to be a force that we've talked about yet. It's not going to be a bond. It's going to be different than a bond, and we won't even call them bonds. To call them bonds would be improper terminology. So we'll call them intermolecular forces. You may also see it abbreviated. I'm going to abbreviate it a lot as IMF. Okay. And again, there are going to be a few types, but they're different than the bonds that we've seen so far. Okay, so there is a difference between the two. Generally, I could say this too. Generally, the bonds that hold the molecule together are stronger than the bonds holding two molecules together, that attraction that we call IMFs. So generally, if we have to compare the two, the IMF is the weaker one. If we add heat if we try to break these attractions, the intermolecular force is going to break first. That's easier to sever than the bond itself. So the intermolecular force is weaker than any bond that we've talked about.